Okay, please, Alessandro, whenever you're ready.
Okay, welcome everybody. I'm very pleased to be here, and I would like to thank Professor Stris for inviting me and giving me the opportunity to present and share this work, which is based on a preprint, which is available on Archive with the same title and done in collaboration with my PhD advisor, Professor Lucio Bedulli from the University of L'Aquila. So the title is SOZ Mirror Symmetry of Solved Manifolds, and it deals with generalization of the mirror symmetry conjecture to the non-Keller setting. We start with a brief outline of the talk. We will first recall what is mirror symmetry, focusing on the Strominger-Yau-Zaslov approach, and then we will see how to extend this approach to the non-Keller setting. Then solved manifolds will enter the picture, and after recalling some results of classification of structure of our interest, we will combine the fine and symplectic geometry of solved manifolds to obtain a recipe that we will use to construct several examples of pairs of solved manifolds that satisfy this non-Keller version of mirror symmetry. And lastly, we will discuss the results obtained and leave some remarks. So, what is mirror symmetry? It was originally formulated for Calabi-Yau manifolds in the context of string theory compactification, and it asserts that for every Calabi-Yau X should exist another Calabi-Yau X check, such that in a certain way, the symplectic geometry of the first should correspond to the complex geometry of the second, and the symplectic geometry of the second should correspond to the complex geometry of the first. This exchange between the two geometries is represented by isomorphism at the level of Dolbeau cohomology groups, and can be pictorially represented by a symmetry along the oblique axis of the correspective Hodge diamonds. Since the 90s, many examples were found, and several approaches were proposed to explain this phenomenon. We will adopt the approach proposed by Strominger, Yau, and Zaslov, which wants to explain the mirror symmetry phenomenon via a torus duality. So this construction relies on the existence of a third space B, over which both X and X check fibers in dual special Lagrangian tori. For all the duration of the talk, we are focusing in complex dimension 3 or real dimension 6. So in the Strominger-Yau-Zaslov construction, one has to start from the symplectic side of the story, and it relies on a famous result in classical mechanics, which is the Arnaud-Liouville theorem, which says that when we have a Lagrangian torus vibration, where Lagrangian means that the symplectic form, when restricted to the fiber, is 0. When we have a Lagrangian vibration between compact manifolds, the fibers must be tori. And also we have a preferred set of coordinates called the action angle coordinates. So for every point in the base, there exists an open set and coordinates R1, R2, R3 called action coordinates, such that the preimage of this open set with the restriction of the symplectic form is symplectomorphic to the cotangent bundle mod a lattice, where the symplectic structure is the canonical one of the cotangent bundle, and this lattice is generated by the differential of the action coordinates. We denote with theta I the fiber coordinates inside the cotangent bundle, and they're called angle coordinates. And also we have that the symplectic form is already written in Darboux frame. One fundamental remark about the action angle coordinates is that they are defined up to an integral affine transformation. That means that we are endowing the base of the vibration with an integral affine structure. In the following, we also assume that the linear part of this affine structure is in the special subgroup. So,
Is there,
Hans, yeah,
what's sort of like the invariant way to, well, is there like an invariant way to make that assumption?
sorry.
I mean, I guess as I understand it, this assumption that you say the linear part is an SL3Z, it
Yeah,
seems like it's sort of depending on the local coordinates, but I guess it's invariant somehow. It's
yeah, but it is required to obtain the, um, the complex tree form on the complex side. Because you need to glue all together the local forms, and you need that determinant should be one, must be one.
so it's like equivalent to asking for a holomorphic volume form on X.
Yeah,
Is that the point? I see.
yeah.
Okay, thank you. Yeah.
Next we are going to dualize this construction, it is required.
Yeah. Thank you.
No, you're welcome. So the next step is to de-dualize this construction. That means we can look at a torus fiber as a vector space modal lattice. We can take the dual vector space and the dual lattice and obtain the dual torus. So we denote with theta check the fiber coordinates inside the tangent bundle of the open set, and these coordinates are dual to the preceding theta i's. This, sorry. Once we have dualized the torus fiber, we can glue together all these tori, and the new manifold obtained is X-check. This can be interpreted as also as the moduli space of flat connection on the torus fiber of the first vibration. This new manifold X-check has a canonical complex structure and canonical complex coordinates given the following way. And moreover, there exists a biholomorphism with a preimage along this new vibration with the tangent bundle, sorry, mod another lattice lambda, which is the dual of the preceding lattice, and this is generated by the coordinate vector field. As I was saying before, with assumption of the affine structures lying in the special linear group, we can form a globally defined holomorphic volume form that induces the complex structure. With this setting, we say that the pair x omega and x check big omega check form a semi-flat mirror pair. In this setting, we can speak about semi-flat differential form, which are non-ideals that a subset of differential forms which locally have this expression. In particular, the coefficients depend only on the base coordinates. So we are in place to define the main tool that realize the correspondence between the two manifolds, and this is the Fourier-Mukai transform. So we can first form the fiber product of the two manifolds X and X check over the base B, and we can define this map between the semi-flat differential forms in the expression, which indeed resembles the classical Fourier transform for function. There are some new characters. The calligraphic P is the polarization switch operator, which simply sends the Z differential to the check theta and the bar zeta to the R. And this happens only in the complex side where there are two different polarization. We recall that a polarization is an integrable subbundle of the complexified tangent bundle of a manifold. And on the complex side, we have two polarization, the complex one induced by complex coordinates and the polarization induced by the dual action angle coordinates. So the polarization switch operator just sends Z to check theta and zeta bar to R. And F, capital F, is a curvature term, and it is the curvature form of the canonical connection of the Poincaré line bundle over the fiber product. The fiber product is also called the correspondence space. And from the diagram, one can understand why this is called it is a Fourier-like transform, because you start from a form in one of the two sides, you pull back it on the correspondence space, you multiply with form, so you wedge with an exponential term, and then you push forward along the other vibration, integrating along the fibers. So this is a very concrete and geometrical description of the Fourier-Mukai transform, which was born in the context of derived categories for abelian varieties. So, in general, the semi-flat setting does not require Calabi-Yau condition or Keller geometries. It's just a relationship between symplectic and complex geometry. But when the manifolds are Calabi-Yau, as in the original formulation, you can do this construction in two ways. You can, since the manifolds are both Kähler, they are both symplectic and complex, and you can use the two different Kähler forms to undo the base with two different affine structure, and both the Kähler matrix and the affine structure are related by a Legendre transform. When moving to the non-Kähler setting, we lose one half of this construction, and this is one of the main differences. So how can we extend this formulation to the non-Kähler setting? In the 2015, Lao Zheng Yao proposed an approach using SU3 structures, which is the datum of a couple of differential forms omega and big omega, such that big omega is a complex tree form that induces an almost complex structure with respect to capital omega is of type 3-0. Omega is a real true form that induces an almost symplectic structure, which is of type 1-1. And as a consequence, we have that the non-vanishing top form that we can define with them, they must be proportional. Combining the two form with the almost complex structure, we get a metric. And also the wedge of the two form is 0. We can observe that if both the forms are closed, one recover the usual Calabi-Yau condition. So if you want to relax the Calabi-Yau condition, we can ask less integrability of the structure. That means one of the two structures cannot are allowed to not be closed. So we can distinguish two different geometries. On a side, we have the type 2a equation, also said symplectical flat, and the other side, the type 2b equation, also said complex balance. And if moreover both the forms can be taken in the subset of the semi-flat differential form, we say that the SU3 structure is semi-flat, eventually of type 2A of, or 2B. In the definition of the type 2A, type 2B equation, also make their appearance the flux terms. Even if we are not going to use them directly, they're important because they encode the information about the torsion of the structure, and also they are defined in terms of the differential operators that are used also to define the geometric PDEs for non-Kähler flows.
Sorry, Alessandro.
Yeah.
What is F in these formulas?
Okay, sorry, I haven't said. It's
It's
just
this.
it's the conformal factor of the structure.
Oh,
It's
oh,
the proportional factor of
oh, okay,
the
yeah. Thank you.
top vanishing form. No, sorry. Thank you for pointing out. Um, in our example on solved manifolds, they will be constant numbers, just scalars. Uh, okay. So in the when assume we have a couple of semi-flat cioè, a semi-flat pair, which is also a pair of semi-flat SU3 manifolds, eventually of type 2A or 2B. We would like to have an analog notion, analog version of the non-Kähler of the mirror symmetry relation also in a non-Kähler setting. So, but since we are no more in the Kähler world, we cannot use more the Hodge theory machinery, and so we have to use some new cohomologies. On the complex side, we can use the well-known Bot-Chern cohomology, which is defined as the the kernel of the RAM operator mod the image of del bar operator. Oh, sorry. While in the symplectic side, we can use the more recent cohomology introduced by Seng Yao, and which is defined as the kernel of the RAM operator plus the d lambda operator mod the image of the d lambda operator. We recall that d lambda in the spirit of Kähler identities is defined as the commutator of the RAM operator with lambda, which is the dual Lefschetz operator. But since we want to have the analog of mirror symmetry, we would like to have a notion of non-Kähler diamond. For the complex side, we have already a PQ decomposition, but what about a symplectic diamond? So in order to do so, we can define a symplectic decomposition by fixing a Lagrangian integrable distribution with a note with delta inside the tangent bundle of the symplectic manifold. This is also called a real polarization. Since we are in the context of a SU3 structure, we have a metric, and we can use the metric to split orthogonally the tangent bundle and extend this decomposition for at the level of differential forms. So we have P direction along the distribution delta and Q along the perpendicular one. And if moreover our SU3 symplectic manifold is a total space of a Lagrangian fibration, it's natural to choose as a Lagrangian distribution the vertical one induced by the vibration itself. So combining the semi-flat setting that gives you a Lagrangian vibration with the decomposition used by the previous slide, we can define the refined Seng-Yao cohomology, defined as before, but intersecting with the semi-flat forms, where the PQ decomposition, we are dropping we are using the delta superscript for denoting the distribution, but we are dropping it because it's itself induced by the vibration. So the subscript B tells us that we are taking the vertical distribution for delta. So we are recalling now the main results contained in the paper by Lao Zheng Yao, and they have proven that the Fourier-Mukai transform give isomorphism as double complexes at the level of semi-flat differential forms that induces, of course, isomorphism at the level of cohomology, and this second set of isomorphism is the non-Kähler analog of the mirror symmetry relation for the diamonds. The other fundamental result,
Can you say again what is APQB?
sorry,
APQB is PQ forms, and then what is the condition with respect to the vibration?
sorry, I didn't understand.
Yeah,
What about B?
APQ sub B are PQ forms, and then what is the condition with respect to the vibration?
We are assuming the semi-flat setting. So um, we have a couple, a pair of manifold X and X check
Yeah,
that are endowed with a semi-flat SU3 structure.
yep.
So okay, the the hypothesis in this theorem is that the X and X check are the two SU3 are two SU3 manifolds, one symplectic, the other is complex, that also fit in a semi-flat in a Strominger-Yau-Zaslav construction.
Yeah. So my question is, in the definition of in this Bochern cohomology that you define, what is the definition of
Okay,
PQ sub B?
okay, no, the B in the Bochern cohomology is just that we are restricting ourselves to the semi-flat forms.
Which are, can you recall what they are?
Yeah, yeah,
So
yeah, of course. In the Strominger of this form, the coefficients only depends on the base.
okay, okay, thank you.
Oh, you're welcome. Okay. The other fundamental result is when you have a semi-flat mirror pair and we choose a 1-1 form in the complex side and we map via Fourier transform on the other side and we call it big omega, then the triple X omega big omega is an SU3 structure if and only if the other triple X check, omega check, and big omega check is an SU3 structure. Consequently, the first is semi-flat of type 2A if and only if the second is semi-flat of type 2B. Also, the fluxes correspond to each other. And the only example presented in dimension 6, complex dimension 3, is the tangent cotangent bundle mod lattices of the Heisenberg manifold, which is indeed a Hill manifold. So the main scope of my PhD project was to find examples of pairs of SU3 manifolds that satisfy all these construction. So it was quite natural to look among solved manifolds, and I will explain why. So
In the theorem by Lao Zheng Yao, they don't use the flux for the T duality, right?
no, they just the duality for the fluxes just follows from the B complex is isomorphism.
Actually, yeah, can I just sort of follow up on that? I mean, yeah, my understanding was always that underlying these like mirror symmetry duality, it's really T duality.
Yeah.
Is it right? And
Yeah.
I mean, my best understanding of this is through like Courant algebroids, like as an isomorphism of sections of some Courant algebroid. And so like what is playing the role of like the H field here?
There is no H field in all the
It's
paper
just always
by,
0 or something.
yeah, there is no H field.
Okay. Yeah.
So, okay. We recall a submanifold is the quotient of a Lie group mod a lattice, which is a co-compact discrete subgroup. So why they are useful to talk about mirror symmetry? First of all, their topology, their structure is suitable to speak about duality because, for example, nil manifolds, which are nilpotently groups mod a lattice, they are iterated circle bundle over a nil manifold, over a torus, while solved manifolds are iterated bundles over tori with solved manifolds as fiber. This is the most of construction. So their topology has a lot of, let's say, circle and tori inside the structure. Then classification results and cohomology computation can be reduced at the Lie algebra level, which is more tractable. Their non-Kähler geometry is already well investigated. We recall, for example, that the first non-Kähler symplectic manifold was the Kodaira-Tarston manifold, which is a four-dimensional nil manifold. And also, in dimension 3, it's already full classified their affine geometry. So in the following, we will recall some results for the classification of the structure. In the nilpotent case, the nilpotent Lie algebra that admits a 2B structure were classified by La Torre, Guarta, and Villacampa, and are 5, while the nilpotent Lie algebras that admit a 2A structure are just 2, and they were this was proven by Conti and Tomassini. Here we remark that for the complex side, the authors give a full description for each of the complex nilpotent Lie algebra. They classify all possible complex structure that admit a balance metric, and also they compute their Botcher cohomology. While for the symplectic flat counterpart, there are only existence results. There is not a full complete classification for a fixed symplectic structure. And this is the same also for the solvable case. Indeed, the solvable, not nilpotent Lie algebras that admit a 2B structure were classified by Fino et al. And Ugarte, while the symplectic flat counterpart has been done by Fernandez, Manero, ut al. And Ugarte. So one of the first ideas was to search among all these solvable Lie algebra for candidates for the non-Kähler mirror symmetry. And we were able to make the pairing for almost all of them according to the non-Kähler construction. So before doing so, before explaining how we were able to do it, we have to recall some basic fact about affine and symplectic geometry of solved manifolds. We recall that a manifold has an affine structure if is endowed with an atlas whose transition function are affine. We say that if the linear part is in SL NR, then the affine structure is special. If instead the linear part is with values in the integrals, we say that the affine structure is integral. And moreover, this is very important, we can associate to an affine structure a pair of maps, the developing map and the Lonomy representation. The first is an immersion from the universal covering of the manifolds into Rn, while the whole map is a homomorphism from the fundamental group of the manifold into the affine group. The developing map can be thought as a globalization for the affine coordinates. When the manifold is itself a Lie group, we say that it has a left invariant affine structure if left multiplication map is affine local chars. In particular, we can define an affine representation the following way as the unique map that make this diagram commute. This map is called indeed the affine representation of the affine structure, and we will denote with rho its linear part and with rho star its dual the dual representation. In the following, we always assume that the group we are working with are unimodular, so we can find a lattice inside, so that we can form the quotient and work with compact manifold. In particular, for the homogeneous manifolds obtained from Lie groups, the restriction of the affine representation to the lattice correspond to the whole map, to the holonomy map for the quotient manifold. So, as we said, we have seen before, there is a relationship between the symplectic geometry and between the symplectic geometry and affine geometry, and this is thanks to the Arnold-Liouville theorem. So, when we have a Lagrangian vibration between compact manifolds from M to B, this induces on the base an integral affine structure. What is very important is that the action coordinates that come from the Arnold-Liouville theorem are precisely the coordinates that are induced by the developing map when seen inside Rn. Moreover, this was an observation made by Doistermatt, already by Doistermatt, is that the matrix that represent the monodromy of the vibration is just the inverse transpose of the linear holonomy of the affine structure. This remark is very important because it is suggesting that by looking at the affine structure of the base, we are able to control how the fibers of the total space are glued together. So by controlling the affine structure, we can control the topology of the total space. So the ingredients that we are used are the following. We start from a three-dimensional, simply connected, unimodular, solvable Lie group G. We choose a complete left invariant affine structure on G. This is equivalent to the choosing an affine representation or simply transitive affine action of the group. We do the assumption that the affine structure is special, so that the linear part lies in the special linear group. We fix a lattice gamma in the Lie group such that the restriction of the representation to gamma is in the special integral affine subgroup. With this hypothesis, we can form the following semi-direct product and we define a six-dimensional Lie group via semi-direct product and six-dimensional lattices. X, we denote this quotient with X and X check, and this is the main result of our work. We can define an action of the six-dimensional Lie group on the tangent bundle of the three-dimensional homogeneous space mod a lattice. This lattice lambda is induced by the affine coordinates, and this action as a stabilizer precisely the lattice defined above, and this realizes the quotient manifold TB mod lambda as a homogeneous space for the solvable Lie group TG. By dualizing everything, you get the same for the T star G and T star B mod lambda star. So we can identify as a manifold, but also as a torus vibration, the X with T star B mod lambda star and X check with TB mod lambda. This is also due to the analysis carried out by Dosselmat, because this identification is possible when the Lagrangian vibration has a section. And indeed, this is the case in our construction. So, in particular, X has a symplectic structure such that is symplectomorphic to the canonical one of the T star B. At the same time, X check has a complex structure represented by check big omega, such that this is bilomorphic to the standard one of the tangent bundle. Moreover, we can define on X a complex form big omega and on X check a real one form omega check, such that they form indeed a semi-flat SYZ dual SU3 pair. So this is the situation we have in our construction, and we give a very briefly a sketch of the proof. Of course, we define the Lie group multiplication on the six-dimensional Lie group via semi-direct product using the linear representation. Then we use this multiplication law to define an action on TB. We dualize everything, and then we define a preferred global left invariant set of one forms by defining first at the identity of the corresponding six-dimensional group, and then extending by left invariance globally. So that the symplectic form has this standard expression in the symplectic case side, while the complex form in the complex side has this other expression. Then we define the requested the remaining differential form in this way, and the very reason why the form defined in this way satisfy the SU3 equation is that by denoting with H a point in the T star G and H check inside TG, we observe that the differential of left multiplication map for the two Lie groups are of this standard form. The first is always symplectic, the second instead is always complex. That means that commutes with the standard complex structure of R6. Sorry, 1 second. So we then applied this theorem to each three-dimensional simply connected unimodular solvable Lie groups. There are only 4 in dimension 3. The abelian R3, the Heisenberg group, which is the group of unitary angular upper matrices with real entries. Then we have the summary group of the Minkowski plane and the summary group of the Euclidean plane, but we will omit the last one because it is not completely solvable. This Lie group can be used to obtain other examples of semi-flat mirror pairs, but we have excluded from the our treatment because the cohomology computation are more involved, because all the results for the cohomology works mainly for the nilpotent case, and in the solvable case, in the completely solvable case with some adjustment, but doesn't work at all for the non-completely solvable case, so we have excluded. But topologically, they can be used to obtain semi-flat mirror pairs as well. So for the first three Lie groups, we fix a lattice. In the first case, we obtain a torus by choosing the subgroup inside the Heisenberg group of integer entries. We obtain the Heisenberg manifold by quotienting. And also by choosing this particular lattice inside the E11, we obtain a compact manifold that correspond to the solid geometry in Thurston classification. So we then have chosen some particular affine structures for every three-dimensional Lie group. This notation, I'm adopting the notation we use in the preprint. So we are denoting the affine structure with the developing map and the linear part of the holonomy representation. And then we used this homomorphism rho and rho star to obtain a six-dimensional Lie group and the corresponding Lie algebra. The choice for the affine structure was done by following the result by Fred Goldman, which is regarding the classification of integral affine structure for three-dimensional Lie groups. So in this table are reported the pairing we obtained with our construction, and they are reported at the level of Lie algebras. And also we have computed the corresponding Bochern-Zhang-Yao cohomologies, providing the first examples of non-Kähler mirror diamonds. In the table, all the nilpotent Lie algebra and the algebra, the first solvable Lie algebra, for these ones, these computations are valid also for the corresponding solved manifolds, thanks to the Nomizu-like theorems that can transport the result for the invariant for the Lie algebra to the invariant cohomology of the manifolds. But for the complex side of the other solvable example, this result is not valid, and some more involved analysis is needed. This is because many of the results concerning cohomology relies on the requires the nilpotency of the algebra, while in the other case, for the other solvable case, there are more ad hoc arguments. But regarding this classification, this pairing, we can observe, for example, that the first symplectic Lie algebra, in the first column, they are the symplectic side, and the mirror is complex. We can observe that the first Lie algebra and the second are the same, but they have two different mirrors. This happens because the base of the vibration is different, and this corresponds to have chosen a different Lagrangian distribution in the same symplectic manifold. So this is an evidence that mirror symmetry, I mean, at least in this with this description, relies strongly on the choice of the base over which we are doing the T-duality. So this is an example of the same symplectic manifold that can fiber in Lagrangian Tori in two different ways, choosing two different base, and the mirror manifold is different. They are not diffeomorphic. For example, in the context of solved manifolds and nil manifolds, if two nil manifolds or solved manifolds are have non-isomorphic fundamental groups, so lattices, the solved manifolds or nil manifolds are not diffeomorphic. Moreover, for the third, fourth, and fifth example, we had a family of affine structure that depends on a real parameter lambda. And we have three different possible diamonds. And this was also interesting because by analyzing the first one with lambda equal to -1, we were able to find another complex balance structure on the Lie algebra 000 E12, E14 plus E23 that were missing from the result of classification. And we were able to do it just by applying Fourier-Mugai transform of the structure in the symplectic side, and we obtained a complex balance structure that was missing. Moreover, another remark, the last one, this Lie algebra is an example of self-mirror. But this Lie algebra does not admit nor a complex balance structure nor a symplectical flat, but it has a symplectic SU3 and a complex SU3 structure that are mirror to each other, and this underlies the fact that mirror symmetry is not an exclusive of symplectical flat or complex balance geometries, but it is a properties of SU3 structure or in general SUN structure. And we can do some final comments and possible ways to go ahead with this line of research. First of all, it's possible to rephrase all the results in terms of generalized complex geometry. Also, one can complete the picture by giving results for classification of symplectical flat structure, because I remark there are only existence results. Also, there is a lot of possibility by applying the symplectic counterpart of currents using the lambda cohomology, and also it's also possible to adopt the approach used by Doisterman and try to understand which kind of affine variance could be related to the presence of a Lagrangian vibration or to the presence having a Lagrangian vibration of a symplectic half-flat structure. And so this is all. Thank you for your attention.
Thanks, Alessandro. Are there more questions? I guess I was curious.
Yeah.
Is there? Oh, go ahead. Go ahead.
No, I was watching.
Oh, sorry. Yeah. Is there a description of SU3 structures in generalized complex geometry? I mean, I guess you have a symplectic form, so I mean, there's
well,
always that.
I found something, but done by physicists, I guess. They talk about SU3 times SU3 structures, and of course they are then described in terms of spinors, but there is something about it.
Huh.
Yeah, there is. I mean, there is a description. It's just a generalized metric and a spinor, a complex spinor in the for the B plus.
Okay. Oh,
I mean,
that's it. That's everything.
and that's it. The B plus needs to be. I mean, you want to you can do it in the exact case, and it's going to be just that.
I see.
And if you want an SU3 cross SU3, then you will have two spinors, one for the plus, one for the minus. I guess.
Okay.
Yeah.
Thank you. I guess another question I had is this
Yeah.
phenomena. So you found two non-diffeomorphic like mirror pairs.
Yeah.
From like the fixed from one fixed manifold. Are there examples of this in the Kähler setting for Kähler mirror symmetry?
I don't know sincerely. In the classical Kähler mirror symmetry, there is another problem that that most of examples, and I guess every example is singular. Instead, in the non-Kähler
Right.
setting, everything is smooth.
Right.
So it's also a good advantage confronting the classical Calabi-Yau, which are defined only locally. You can define only locally the T-duality. Of course, this is thanks to the simplified structure of solved manifolds. But no, I don't know if in the Kähler setting there is something similar. I guess not, but I'm not sure because in the everything I read studied about the classical Kähler setting is always something that locally is a cotangent and tangent bundle.
Right.
So I don't know.
Yeah, and I guess I was under the impression that in that setting the mirror was thought to be unique. I mean that, so it's somehow interesting.
Yeah, what is interesting that changing the base, you are changing the Lagrangian distribution, even if the symplectic manifold is the same, the change of Lagrangian distribution makes some jumps for the PQ cohomology in Zhang-Yao cohomology.
I see.
Even if the sum of the PQ is the same, there is some jumps inside the PQ.
I see. I see. Any more?
I have perhaps, yeah, sorry. Go ahead, Mario.
No, please go.
Yeah, I have a question. Well, I don't know, maybe it's a naive question, but I was wondering if these techniques can also be applied to two complex dimensions and SU2 structures, because I guess in the Calabi-Yau setting, in that case, the Kähler setting, in that case, you only have K3 surfaces, but if you allow now for non-Kähler things, maybe there's something non-trivial.
I've tried using the Kodaira test on nil manifolds, but this is really less interesting because it starts to be interesting when the base manifold is at least three-dimensional. This is due to the fact that in the Lagrangian, it was observed by Deutstermat. In the Lagrangian fibration, all the information is encoded by the second cohomology group of the base with values in the lattice.
Okay.
So it starts being interesting from dimension 3. This is a very topological reason why you should look from dimension 3 and so. Moreover, I haven't said it, but the construction we used for Lie groups can be used in any dimension. It's very general, but we applied in dimension 3, but it's very general.
Okay, yeah, that's great. Thank you, Alejandro.
Oh, you're welcome.
Yeah, my question is related to these three form flags. So you're saying in your, I mean, you are T-dualizing in a way, like ignoring the existence of the three form flags, but in type 2B theory, the three form flags is, if I'm not mistaken, the DC of the Kähler form. In your case, is never closed because otherwise you will have Kähler. So So this is maybe more a general question for the audience, but so what happens if I have a type 2B background with NS fluxes, but an NS5 brain source? So the DC of omega is not closed. It is some source. So how do I T-dualize? Is there something in the literature that tells you how to T-dualize that? Maybe Mateo or Friedrich can do their magic.
I'm not very experienced with the language of brains and sources and math. I'm sorry.
No, yeah. The point is, I want it's a general. It's not specifically for you, Alessandra. I'm just posing this question
Don't worry, don't worry.
to the audience. That is there a recipe for T-dualizing type 2B when you have a three-form flux which is not closed?
Yeah, I don't know on the top of my head. I feel like there must be something in the physics literature for sure. I don't know how useful or how precise. I don't know. Yeah, I really don't know.
An interesting question.
Yeah, I'm really curious that you actually like you ignore the three form, but actually you match the cohomology. So I think it's very interesting, but there should be some way of fitting your picture into the physical notion of T-duality with flux or something. I don't know. It's mysterious to me.
I mean, I guess if at least locally you can use some kind of probably some type of Boucher rules adapted to that situation, right? You can express like your three formats coming from certain B field. Maybe you can just use certain Boucher rules that would tell you how things transform locally, non-trivially. But I don't know.
I mean, well, like morally, the DDC of the Keller form should be localized because it's like the source for a five brain, right? So there should be some limit morally where this is localized, and then in the complement of this place where this is localized, then this is a closed free form, and then you can do ordinary T-duality, and maybe you need to correct it somehow.
Yeah.
Using the locus where it's singular, but
right.
It's just I guess.
Yeah.
Okay. Well, are there more questions? So, okay, yeah, let's thank Alessandra again for the nice talk.
Thank you.